Alright, hey guys. Today we're going to learn about rotational inertia. It's similar to normal inertia, but it deals with circular motion, not translational motion. But before we learn it, we gotta go over torque. Torque's really important when going over this. So torque equals force times lever arm. In this case, we have a circle, an axis in the middle, and we have a particle on the tangent of the circle. The radius is the distance between the axis of rotation and the particle. However, if we're trying to find the torque of this particle, we cannot use force times lever arm. We have to derive a new formula so that we can use different values. So force equals mass times acceleration tangent. Acceleration tangent equals radius times alpha. Alpha in this case is angular acceleration. And radius of the particle equals the lever arm because it's not translational motion. If we combine all these new formulas we just learned, we get a new formula for torque. This formula is torque equals force times radius. You can further rewrite this, and you get mass times radius squared times alpha. And finally from this, we can sum up and get sum of torques equals sum of mass times radius squared alpha. These three formulas I'm unboxing right now are really important when it comes to rotational inertia. Alright, so to recap, we have the sum of torques equals the sum of mass times radius squared alpha. We can plot the sum of mass times radius squared part, and I'll go back to that later. The alpha is constant for all particles in a rigid body. And I equals rotational inertia, or it's also known as moment of inertia. And with the part we just pulled out, we get I equals the sum of mass times radius squared. And you can also plug that into torque, and you get torque equals I times alpha. From this, we finally see formula-wise what rotational inertia is. Well, we saw what rotational inertia is like through formulas and stuff, but even I'm kind of confused. Like, what is it really like? Even seeing the formula, I don't really understand what it is. So we're gonna illustrate a little bit like what it really is. So here are some cylinders. One has a bigger radius than the other, but they have the same mass. The one with the bigger radius has a higher inertia, which makes it harder to start or stop moving. We can use this concept in a real life example, like trapeze performers who walk along a single tightrope. They'll usually hold a long rod also, but people usually think like holding a long rod will make it really hard to maintain balance. But the thing is that using the concept of rotational inertia, the rod acts as radius, which a really large radius allows him to actually have higher rotational inertia. This makes it a lot easier for trapeze performers to stay on top of a rope and maintain balance. So the reason why they hold the rod is actually not because it's more dangerous, but it's a lot safer because they can easily walk on top of the single rope with that really long rod. Alright, so basically that's what rotational inertia is. You know, if you still don't get it, just imagine like, would you rather have like a big wheel or a small wheel like coming towards you? Like the small wheel you could probably stop, but the big wheel has like a larger rotational inertia, so it'll probably crush you or something. You know, same thing if like you wanted to start or stop like a wheel. Like if it was smaller, it'd be a lot easier to just make it move than like a bigger one. It's basically just like inertia, just like in a circular motion. Well, that's our video. Thanks for watching. Don't comment, rate, or subscribe. We don't need subscribers. Hey, 6 Flags was pretty fun. Alright, bye.